Okay, we're continuing on here, chapter 7, I believe. So last time we started talking about stoichiometry. Before that, obviously, we talked about balancing equations and types of equations. We then talked about really moles, atoms, Avogadro's number. So at the end last time, we sort of put both of those things together in what's referred to as stoichiometry. And remember, stoichiometry is really nothing more than sort of a conversion problem. The main difference is instead of maybe going to a table and sort of looking up a conversion factor, where you get the conversion factor is from the balanced equation. And it's just the coefficients from the balanced equation, which represent what is referred to as the mole-to-mole relationship between the two things. The reason you need to do that is typically in stoichiometry problems, you are given some information about somebody in the reaction that you're really not interested in. You're kind of interested in somebody else in the reaction. So you need a way to kind of convert from maybe a reactant to a product to a reactant to another reactant, or a product to another product. And the way we do that, the rule sheet is coming down today. As I know, it usually goes up. It's coming down today, so that is the way it's going. So we do get the relationship really from the balanced equation. And when we do stoichiometry problems like we finished up on last time, you could really kind of boil them down for our purposes, really the four sort of basic steps. And you just kind of want to do those in order. For example, the first step always, and none of this works, is you got to start with a balanced equation. So if you don't have a balanced equation, you're going to have the wrong mole-to-mole relationship, and obviously nothing will be right in terms of your calculation. So if you're given an equation, you do want to take a second just to make sure it is balanced. Probably if you do see numbers in it, it's most likely balanced for you. But if you definitely don't see any numbers in the equation, you should definitely take a really hard look at it and make sure that it is balanced. Once you have a balance, pretty much the next step you want to do is whatever they gave you, you want to convert into moles. So very often what they give you is in grams, but it could really be any unit that they want. So whatever unit that they give you, you got to get yourself to moles. Usually that involves a step along the way, if not directly, going from grams to moles. And we use the molar mass from the periodic table to do that. Now that you have whatever they gave you basically converted into moles, the next thing is really the big stoichiometry step of the calculation. You're going to go to the balanced equation and find the mole-to-mole relationship. So what you're trying to find is really two basic things. One of the things that you should be looking at in the equation is pretty much whatever they gave you. So whatever sort of reactant or product that they gave you, that is what you should do. The other thing is basically what you want to find. So those are really the two things that you should be looking for. Remember, that will give you some type of mole-to-mole relationship. For example, if we were interested in lithium and water in this above equation, it would be 2 moles of lithium gives you 2 moles of water. That is nothing more than really just the coefficients from the balanced equation. And as we talked about last time, that will set you up 2 possible conversion factors that you technically could use. And you won't use them both as we saw, but you will use hopefully the correct one here. And once you do that, that really is sort of the stoichiometry part of the calculation. You will then be at step number 4, which means if you did everything up until that point correctly, the units you are in are moles at this point. So not in all problems do you want the answer to be in moles. Sometimes you may want some other unit. Again, very commonly at this point, going from moles to grams is a very common sort of conversion that you have to do at the end. Also, obviously, using the molar mass from the periodic table. But really, it could be any unit they want. If they want the final answer in pounds or kilograms or any weird unit that they so choose, it may involve at the end there multiple conversions to do. But very commonly, since grams is typically the thing we use to measure out and stuff like that, a lot of times it is sort of grams. Now, these are really the same 4 steps you should do in any of these type of problems, no matter, again, as I mentioned, maybe how scary the equation looks, the numbers look, it doesn't really matter. You pretty much just roll through these steps in this order, and you should get you to the right answer. The other thing that is a very common mistake that, again, some people make that I might have mentioned last time is, again, you don't want to undo any of these steps. So, if something's done for you, you just go forward, don't undo it. I've seen people, for some reason, they're given something in moles, they decide they need to convert it to grams, and then they convert it back to moles. So don't go backwards. So if something happens to be done for you along the way here, you just want to kind of continue forward until you go through there. Again, sometimes you may not have to do the 4 steps. Sometimes you may need to do the 4th step, but really just have this as sort of a checklist when you come to these problems, as this is what I need to do, this is what I need to do next, and so forth. And again, it should lead you to the end there. Any questions on any of that stuff there? All right, so we did one in this example last time. So why don't we do the same equation here, but in this case, we want to know how many grams of H2 can be formed by the reaction of 81.75 grams of lithium with water. And again, I'll give you some information from the periodic table. Lithium 6.941 and hydrogen 1.008. All right, so take a few minutes here, follow those same 4 steps. Again, if something is done for you, continue on. Yeah. Okay, let's take a look and see how you're doing. And again, I can't repeat it enough. It is the same 4 steps. So that is how I'm going to do it here. And I've been doing it a while. Step number 1 is balanced equation, which in this case is already done for us. So we're good to go. Step number 2 is to convert it into moles. Do I need to do that in this case? I do. What they gave me is in grams. So to do that, I'm going to use the molar mass from the periodic table, hence the box there. So that is the second step we want to do. We want to take what they gave us, which in this case was already in grams, which makes it a little bit convenient. We're going to use the molar mass from the periodic table. Opposites cancel, so we do need the grams on the bottom, basically dividing. The grams here will cancel, and that will get us there 81.75 divided by 6.941, and we'll call it 11.78 moles of lithium. So that's the second step. We're in moles, and really the reason we need to do that at that point is for the third step that we need to do. The third step is to find the mole to mole relationship. So obviously, one of the things that we're interested in is what they gave us, which in this case is lithium. The other thing that we're interested in is what we're trying to find, which in this case is how many grams of H2, which is right here. So this is where we're going to get our mole to mole relationship from the equation, nothing more than the coefficients. That tells us for every 2 moles of lithium I toss in there, I'm going to get out how many moles of H2? 1 mole of H2. Coefficient really in front of H2 is 1, so that is where that comes from. That gives me 2 possible conversion factors. 2 moles of lithium over 1 mole of H2 are 1 mole of H2 over 2 moles of lithium. Now that I have my mole to mole relationship, I'm good to now get rid of lithium because this is really not what I'm looking to find. So we will take our number from above, 11.78 moles of lithium. And in this case, I should use conversion factor on the left or on the right. Should use the one on the right since we want to get rid of lithium. Again, opposites are going to help us that. That's going to give us 1 mole of H2, 2 moles of Li. This is the big stoichiometry part right there. We're going to cancel out the moles of lithium, for which if we divide it here by 2, gets us approximately a 5.89 moles of H2. Any question on that part of it there? Yeah, H2.
Over one mole of H2 and 2 moles of lithium. You end up getting 11.78.
No, I end up getting 5.89 on this part right here. Yeah. The step before that's where the 11.78 came from, is when we converted the grams of lithium into moles using the molar mass from lithium. Other questions on that? Yeah.
Step 2, where did he cross off grams and lithium?
Because technically this is the molar mass, the 6.94 of lithium, so that's technically grams of lithium. I just didn't write the lithium next to it, but yeah. Other questions? Okay, so is this the answer I'm looking for? No, it's close to what I want. I've said now successfully using stoichiometry got us to H2, which is what we want, but we're in the wrong units at this point, right? We're in the units of moles. So we do have to do step number 4 here, which is to convert those moles into something else, which in this case, we now want to convert our moles to grams, which is what we're looking for. In order to do that, I need the molar mass, but in this case, I'm now at hydrogen, so I need the actual molar mass of hydrogen to do that. I don't want to use the same molar mass from above because that was for lithium. So to get the molar mass of H2 from the periodic table, 2 times 1.008, and that gives us a 2.016, I believe. 2.016 grams per mole. We're going to use that like we did earlier as a conversion factor, carrying on with our same number here. 5.89, I'll add a 0, moles of H2 using the molar mass. In this case, we're actually going to multiply by it so that the moles cancel. The moles of H2 will cancel in this case, and we will end up with 11.87 grams of H2 in this particular case. Any questions on that there? Yeah. Yeah, you don't have a number given to you. So there's a concept that we do not get into in this class, which is known as limiting reagents. And basically what that means is when you do a reaction like this, say the lithium in the water, one of them will get used up first. In this case, it's implied because they only gave you lithium's information that it actually will be used up first. You have what's known as excess amount of water, plenty. It'll still be there at the end of the reaction. You have tons of it. So we really don't do any limiting reagent type problems in this class, which is a little bit more complicated than these. So in this case, you will be given really just one piece of information, and it could be a reactant like it was here. It could be a product. And just so you know, you don't necessarily have to cross over the arrow, if you will. When doing stoichiometry, you could stay and do a calculation between 2 reactants. You could also do calculations between 2 products, or you could go from, across the arrow with products to reactants. So sometimes people think you always have to have like a relationship where you cross the arrow. You don't. You can have a relationship where you just kind of do it between these 2 guys, or just between those 2 guys as well. So you could do stoichiometry with anybody in the equation. Doesn't matter if they're both reactants, doesn't matter if they're both products, as long as you have one piece of information, you could do it. So really what this means in terms of the numbers is if you did this reaction and you tossed in there 81.75 grams of lithium and everything went perfectly well, no side reactions, again, you didn't drop anything on the floor, you should in theory produce 11.87 grams of hydrogen gas as a result of this reaction, which is sometimes referred to as the theoretical yield. That's theoretically how much you should get. When you actually do the reaction, you probably won't get that exact amount, but in theory, that's how much you should produce. Again, it really is these same 4 steps. Any questions on that? Let's try another one here. All right, let's do this one. If 765 grams of C6H12O6 is consumed by the body, what is the mass? So we're looking for grams of CO2 that would be produced in this case. I'm going to give you some info that will be helpful. Carbon from the periodic table, 1201. Hydrogen, 1.008. Oxygen, 16. I think that should be all you need. All right, again, even though kind of a scarier looking equation, some bigger numbers, it is still the same 4 steps. So start with the first step and continue on, see what you come up with. So step number 1 is to balance that equation. I do see coefficients, and if you do go through it, it actually is balanced, so that's good. Step number 2, right, is to convert to moles. And do we need to do that in this case? We do. Again, what they gave us was in grams, so we want to convert to moles. In order to do that, we do need to go to the periodic table and get the molar mass. So we're just going to add up all the parts there. So that is 6 times 12.01 for the carbons, plus 12 times 1.008 for the hydrogens, and 6 times 16 there for the oxygens. Gives us a molar mass of about 180.2 grams per mole for our C6H12O6. Obviously, we're going to use that as a conversion factor to convert the grams that they gave us into moles. So just like we've done in the past here, 765 grams C6H12O6. Here again, opposites cancel, which means we do need to put the grams on the bottom so that they do cancel. That means we're basically dividing by it. And when we do, the grams will cancel, and that will get us a 765 divided by 180.2. Looks like a 4.245 moles of C6H12O6. Any questions on that so far? Now we come to the third step, which is again really the stoichiometry step. So we want to go back to our balance equation, find the 2 things we're interested in. So clearly we are interested in this guy because they gave it to us. And in this case, we are trying to produce how much CO2. And from the equation, just picking out the coefficients there tells us for every 1 mole of C6H12O6 I throw in there, I am going to get out 6 moles of CO2. That is again where we could get our 2 conversion factors to use, which again would be 1 mole of C6H12O6 up on top, 6 moles of CO2 on the bottom, or you flip it, 6 moles of CO2 up on top, and 1 mole C6H12O6 there on the bottom. So we are continuing on with the number that we got in step number 2, and that would be 4.245 moles of C6H12O6. Here we want to use the conversion factor there on the right. That puts our guy on the opposite location. And up on top should go 6 moles of CO2. This again comes from the balanced equation. It's nothing more than the coefficients. And this is the big stoichiometry part right there. That's going to cancel out those glucose that we're not interested in. And that will get us 4.245 times 6. We'll call it 25.47 moles of CO2. Any questions up to there? Again, we get to the point where we have successfully got to CO2, which is our goal. but our goal is not moles of CO2, it is grams of CO2. So we do need to do the fourth step, which is to take that number we just got and convert it into grams. Again, we got to remember at this point that we have now converted over the CO2. So we do need to go back to the periodic table and get the molar mass for CO2, which for CO2, it is a 12.01 for the carbon plus 2 times 16 there for the oxygen gives us 4401 as our molar mass for CO2. So we're going to use that to finish out our calculation here, 25.47 moles of CO2. Again, putting the moles on the bottom so that they cancel. And the grams will go up on top so that we are left with it. And at this point here, we will times it by 4401, getting us approximately 1121 grams of CO2. In terms of significant figures, it really should actually be only 3, as that's the only number we have, which gets us to about 1120 grams of CO2 would be produced in this case. Any question on that one there? I'm hoping you can see a pattern that I am not lying to you. It is just 4 steps in a row. Yes, and that is how you should break it up and do these problems so you don't miss a step or miss doing any of it. Any questions on any of that? For the most part, your 2 conversion places are going to be the equation to do the stoichiometry part and the periodic table to get the molar mass, or 2 common places that you will get sort of our conversion factors. Any questions on any of those steps there? Again, means the same thing. Means if we threw in there 765 grams of our C6H12O6, we should produce about 1120 grams of CO2 in this reaction if everything went perfect. Things don't go perfect in real life, so you probably, again, will not produce exactly that, but that is your maximum amount of product that you should produce. Any questions on any of those? Yeah. Yeah. Yeah, so that's the molar mass. So when we get molar mass, that's really our conversion factor, as we talked about earlier on in this chapter, of going between grams and moles and grams. And whenever you calculate the molar mass of something, it is how many grams there are always per 1 mole. So we don't usually put the 1, but the number always stays with the moles part. And it's always per 1 mole when you use it as like a conversion factor. Yeah. And again, a lot of times people won't write the 1 on the bottom. It's just assumed as 1. Yeah. So I'm sorry, say it one more time. In part, which one? Yeah. Right, that's the molar mass of CO2, right? Yeah, so when we calculate the molar mass, it is based on the actual formula. So in step number 2, what we were actually dealing with was not CO2, it was this guy, which is where the 6 carbons come from and the 12 hydrogens come from and the 6 oxygens come from, because that's basically what we started with. So that is what we needed the molar mass with at that point. By the time we got down to step number 4, because step number 3 is the stoichiometry part, which took us from the C6H12O6 to the CO2. That was the whole point, really, the stoichiometry part, to get us kind of over there. Now we're at that point at CO2, so we have to use the molar mass for CO2 in that particular case. Yeah. And another good question as well is sometimes people, when they go to calculate the molar mass, especially in situations like this, for example, the CO2 has a 6 in front of it. So when they go to calculate the molar mass from the periodic table, they'll do it like times 6. And you never want to do that. So whenever you're going to get the molar mass of something, regardless of whatever the coefficient is in the balanced equation, the molar mass should always be based off of just the formula by itself. So just the one formula by itself. We take care of the 6 right there when we do the stoichiometry part. So you don't want to do it down here when you're doing the molar mass. Otherwise, you did it twice. So a good thing and a very common mistake people make is like, oh, it has a 6 like in front of it in the equation. When I go to the periodic table to calculate the molar mass, I should do it by 6. And you never want to do that. So no matter what the situation is, if you're calculating molar mass, to use it as a conversion factor, it should just be based off the formula by itself, regardless if it's in an equation that's got like a 20 in front of it or whatever it may be. You ignore that. You do it based off of the formula. And if you need that 20, where you would use it is in like stoichiometry is where you would use it. So that's also a very common mistake that sometimes people make, is in the calculating the molar mass. And that's why when we say molar mass is how many grams per 1 mole of the substance. So that's basically the formula by itself is what you want to calculate. Other questions? Okay. All right, we're having fun now. Yes. All right, let's try another one that just looks crazier. All right, see what you come up with on this one. They were nice enough to give you the molar mass themselves, so you don't have to calculate it. So this is the molar mass for up here, and this is the molar mass from the periodic table for here. All right, so again, even though big numbers, equation looks crazy, do the 4 steps. See if you get the answer there at the end. So we're looking for how many grams of this guy over here. If we start with 0.7752 grams of that guy. And again, the molar mass from the periodic table already given to you, so you can use those numbers. Look, so again, don't mean to be a broken record here. We're going to start with our first step, which is balance the equation. Again, it was done for us here, so that is good. Second step, as we talked about, is to take what they gave us, which is this guy right here, and convert it to moles, which we do need to do. In this particular case, they were nice enough to give us the molar mass. This normally would be gotten from the periodic table if it obviously was not given to you like we did in the previous problem. Just add up all the parts, and again, that is where that would come from. 2 potassiums at 3910, a PT at 195.1, and 4 chlorines at 35.45 each gives you 415.1. So that was nice that they gave us that. So we will do our first step, which is 0.7752 grams of this guy here. Using that molar mass like we've done previously. Again, we're starting with grams, which technically are up on top. So on the bottom, again, should go grams so that they cancel. And up on top would be our moles of K2PtCl4. Again, the grams here will cancel. And that will get us 0.7752 times, not times, divided by 415.1 gets us a 0.00186, and I'll call it 8 moles of our K2PtCl4. Any questions on that so far? Yeah. I personally would take it to a few digits here and kind of clean it up at the end. Actually, it's going to be about 4 sig figs at the end anyways, but somewhere around that place would be right. Other questions here? Okay, so step number 3, again, is the big stoichiometry spot. That is when we go to our balanced equation and we basically find the 2 things we're interested in, which in this case is obviously what they gave us. The other thing is obviously what we are trying to find. In this case, it is a 1 mole of K2PtCl4. Again, that is just the coefficient in the equation, equals 1 mole of PT and H3 to Cl2. In this case, it makes the math pretty easy. We will do that step, 0.001868 moles of K2PtCl4. In this case, again, we want to go opposite. So up on the bottom there, I guess not up, but down on the bottom would be 1 mole of K2PtCl4 and the 1 mole of the PtNH3 2Cl2. Those guys are then going to cancel. I think I could do this math here. This is going to be 0.001868 moles here of our PtNH3 2Cl2. Any questions up to that point? Again, it happens to be a 1-to-1 relationship, which again makes the math pretty easy. We are again at step number 3, which at this point, if you did it correctly, you should always be in moles. And that is why step number 4 is sometimes needed. And it is needed in this case, since we are again looking for grams. So we do want to convert the grams of what we just, the moles of what we just got into grams. Again, they were nice enough to give you the molar mass of that guy. If they didn't, you would go to the periodic table, 1 platinum, 2 nitrogens, 6 hydrogens, and 2 chlorines in that case. So step number 4 here, taking our 0.001868 moles of our PtNH3 2Cl2. In this case, we want to actually multiply by the molar mass, which is 300.1 grams per mole. The moles will cancel. That is going to leave us grams, and that will get us times 300.1. It looks like it will get us a 0.5604 grams of this guy would be produced in this reaction. Again, same 4 steps, even though it looked crazy, the equation, the numbers, it is balanced equation, converts the moles, mole to mole relationship, and then convert the moles into some other unit. You can't usually go wrong if you just follow those 4 steps. And do them correctly would be good as well. But if you follow those 4 steps, do them correctly, it should end you at the right spot. Any questions on stoichiometry, how to handle these type of problems? So people, again, do a lot of weird things. They try to make it more complicated than it has to be. Just follow the steps, and it should get you to the end. All right, that should wrap up chapter 7, if I'm not mistaken. I think we're out of examples at that point. All right, any questions on chapter 7? Yes, sir. Yeah.
So you just take
Yeah, so pretty much in chemistry, if there's not like a number written, it's assumed to be 1. Yeah.
First portion of we have.
The-
Don't know you know how to write this.
The
Portion on this side, and the first portion on this side, that would determine the mark.
the mole-to-mole relationship is determined strictly from the coefficients, the numbers that would come in front of everybody. So that is exactly where we get all those values from. It's just those coefficients. So if we were doing KCl, it would be 2 moles of KCl. If we were doing the NH3, it would be 2 moles of the NH3. It is based on the coefficients from the balanced equation, which is why every single step that we did for number 1 is always the same. You've got to start with a balanced equation, because if you don't start with the balanced equation, you will not have the right mole-to-mole relationship when you hit number 3, and then thus you would not have the right answer at the end. So, and it is just nothing more than a simply from the equation. It has a 4 in front of it. That's how many moles it is. Or it has a 2 in front of it. That's how many moles it is. Once you balance it, that number in front would represent how many moles of whatever comes behind it. Yeah. Other questions on that? Okay. So we're going to roll to chapter 9, like I said the other day. Let me just give me a sec to get it up and going here. Okay, we are rolling here to chapter 9, which is solutions. So we'll get into some of this, which hopefully will be helpful for next week's couple next weeks. That makes sense. The next couple of labs, I think, involve solutions next week and after spring break. So let us talk about this here. So let's talk about a solution. And a solution really is a homogeneous mixture. And if you remember, homogeneous mixtures basically mean that after sufficient mixing, everything looks the same throughout. And a homogeneous is something like, again, like salt water and stuff like that. Now, aqueous solutions are typically the things when you look at formulas will have actually the AQ symbol next to it. The AQ symbol stands for aqueous. And sometimes people are confused about, but isn't that kind of the same thing as like the guy that gets the L for liquid? A solution is in the liquid state, but there is a difference between something that is a liquid and something that is aqueous. Typically something that's aqueous, you typically make by taking something that's a solid a lot of times and dissolving it in something like water, for example. So if we had something like water just by itself, that is basically a pure liquid. So that gets the L symbol. If we take then water and mix it with some solid sodium chloride or salt, that sodium chloride will then dissolve in the water. And when that does, we get what is referred to as an NaCl that gets the aqueous symbol. It becomes a saltwater solution or sodium chloride solution. So anything that has the L is basically a pure substance by itself. There's nothing else with it. So just water by itself is the liquid. Anything that is aqueous is basically a mixture, which means you got to have at least two or more substances that came together. If you remember our definition there of a mixture, and that is basically what a solution is. All the sort of reagents that you take in lab and use, those are typically all solutions. They are made by taking something, a lot of times water, and adding some other stuff to it to make it. Now, a solution actually has two parts. One part of the solution is the smaller part that is known as the solute. And that is usually the thing that gets dissolved in the larger part of the solution, which is the solvent. So in my example there on the bottom, the sodium chloride would be the solute. The water would be the solvent. As we'll talk about, water is a pretty good solvent for a lot of things. It's actually not a good solvent for everything. There's places where water is a really bad solvent, but water is used a lot of times, especially with ionic compounds. It's a very good solvent for it. It's non-toxic, have a lot of it, they say, yes. And so we use it, a lot as a solvent. But again, a solvent can be other things. For example, you could have a solvent that's nitric acid. You could have a solvent that's an organic compound like hexane or something like that. So solvents really could be anything. And we'll talk in a later chapter how you sort of pick what would be a good solvent and what wouldn't be a good solvent. But again, a lot of times water is a very common solvent. So solution, two parts, the solute and the solvent together make basically a solution. And here's an example of that. Here, the water is our solvent. The copper 2 sulfate here, the blue circles there is our solute. And you can see once we kind of put it in there and start mixing, we get this nice, pretty blue solution, which would be an aqueous solution in this case of copper 2 sulfate. So sometimes people ask, how do you know what the solute is? The very simple answer is, it's the name of the solution. So copper 2 sulfate solution, the copper 2 sulfate would be the solute, and a sodium chloride solution, the sodium chloride would be the solute. So the name of the actual solution is really what the solute is. The water part's implied, like down in this guy in the aqueous part of the solution. So as I mentioned, water is a very good sort of solvent. And it's really because for a lot of things, especially ionic compounds, and it really has to go back to when we were talking about bonding. So water is a polar molecule. And because water is a polar molecule, what that means is it has a separation of charge. So the oxygen side of water, because of the unequal distribution of electrons, is actually more negative. The hydrogen side of water, because of that unequal sharing of electrons, is more positive. And that works really well when you take something, for example, like sodium chloride, which is a sodium ion that's positively charged. So what happens is opposites attract. So the positive charge of the sodium and the negative side of water are attracted to each other. So what ends up happening is the water basically starts to surround all of the sodium ions in solution with its oxygen side, which is negative. Same thing happens if you have the chloride ion floating around. It is negatively charged. And why water works so well, it has a positive side, which is the hydrogen. So water also surrounds something like chloride, which is negatively charged, but it is actually the hydrogen side of water that surrounds it. And that is why when we take something like salt and put it in water and stir it, it looks like the salt disappears, right? It goes away, it's gone forever, but it's actually a physical change. It just disappears to our eyes because there is lots and lots and tons of water molecules that just surrounded all those ions. We can no longer visually see it anymore. It basically all gets trapped in the matrix of water. We know this is true because if you didn't do it in lab yet, and maybe in the next couple of weeks you will do it, you'll take some salt water and you'll heat it up. And when I heat up the salt water, all of the water molecules that have surrounded all these ions will evaporate away. And what will happen is now the sodium ion has nothing to keep it from the chloride ion, and they will come back together. And you will then see the salt reappear in that form. And so the water actually acts as two sort of important things. It allows the sodium chloride to dissolve, and it also keeps those ions away from each other. The attractive force between an ion that's positively charged and negatively charged is a super strong attraction. So without the water there, they're just going to come back together. And again, that's why you would see the water, the salt come back if you evaporate it off the water. This has helped because when we usually take something that's ionic and solid and try to dissolve it, we typically take something and start to stir it, right? When we start to stir it, we're doing two things. We're throwing a bunch of water molecules right on that solid. That's going to initiate this process of basically the water molecules grabbing all the salt. And we're also providing energy, right? As we kind of stir it, right? That helps all that sort of happen a lot faster than if you just dumped it in. And that's essentially what happens and how something dissolves to make a solution. Basically, those water molecules come in and start plucking off those ions, start surrounding the ions. And like I said, by kind of mixing and stuff like that, you help that process along as well. Here's another picture of the same idea. Water molecules coming in, basically plucking off the ions. And again, at some point, we won't be able to see it anymore because all those ions are now surrounded by lots of water molecules. Third picture, in case you hated the first two. All right. So let's talk about solubility in water. If something is soluble, what that means is it basically will mix, right? So we talk about solubility. If we're talking about a solid in a liquid, that means that the solid will dissolve in the liquid. If we have two liquids mixed together and they're soluble, that's sometimes referred to as being miscible with each other. That will just look like one liquid, right? If they both mix. So if you put two liquids together and they're soluble in each other, it will just look like you have one liquid in there. If something is insoluble, that means that the solid would not dissolve. If we're talking about a solid in a liquid. And if something's insoluble and it's a liquid, what you would see is actually layering happening between the different liquids. They really wouldn't mix. Somebody would come to the top, somebody would be on the bottom in that type of case. That is what's sometimes referred to as being immiscible, if we're talking liquid on liquid action there. And if they do mix, it's known as miscible or soluble or insoluble. So when we talk about water, which is polar, pretty much if it's an ionic compound, it will do the exact same thing with some of those pictures. it will definitely be soluble in water. We would expect it basically to mix. There's also some things that are not ionic that are also soluble in water. We know that if we take sugar, sugar obviously dissolves in water, right? We put it like our iced tea or whatever it may be. And ethanol as well. So why is sugar and ethanol sort of soluble in water? It has a lot to do with what those guys have on there. They both basically have kind of the same bond. They have an OH bond, which if you remember from bonding is a polar bond, which basically means that the oxygen is more negative here. The hydrogen is more positive. And that works really well with water, which pretty much has the exact same bond. And that gives a place where water can interact with these guys that are not ions through the same sort of interaction. The hydrogen from water are attracted to the negative oxygen there. This makes what is known as hydrogen bonding occurring. It's a bond between hydrogen and oxygen here. And that allows something like sugar, which is a little bit bigger of a molecule, but as we'll see a picture of it in a second, it is pretty much littered with OH groups all over it. So everywhere that molecule has an OH groups, it gives it the ability to interact well with water. And because there's a lot of OH groups, it's able to interact really well with water. Ethanol as well. Ethanol pretty much looks like this. Little organic guy we'll talk about when we get into organic. And again, it has that OH group right there, which allows it to interact well with water. So here's an example of that. This is actually what is known as methanol. And it also, again, has that OH group, which allows it nice interaction with water. It's able to hydrogen bond with water, which means they will mix really well together. These are actually kind of two liquids here. They would actually mix really well. And again, it would all look like one phase, basically. You wouldn't see different layering that would occur. And there is ethanol, again, with his polar OH group, able to interact well with basically water through positive, negative attraction. So what about oil and water? Do they mix? They really don't mix for a couple of reasons. And the reasons are when we look at oil, basically oil is expensive. Now oil is, a lot to tell me about. All right, a lot of carbons and hydrogens pretty much. Yes. Especially that one called octane. All right, so there's a lot of carbons and hydrogens here. Carbon and hydrogen is a non-polar bond. So it's a really big molecule oil. It has pretty much all carbons and hydrogens, which makes it non-polar. And if you remember from non-polar, what that basically means is it has an equal distribution of electrons. Everybody overall is sharing electrons really well. Essentially, it's like a neutral molecule. It has really no sort of charge. So when it tries to interact with water, which is polar, water really wants to use hydrogen bonding to interact, like we just saw in the previous picture there, where the hydrogen bonds to something like oxygen and they have that positive negative attraction. Because something like oil, which is really has no charge, it has really no long way to interact well with oil. And it can for a short period of time, but it can't maintain that interaction. So if you ever seen like an oil spill, for example, in the water, the oil typically ends up floating on the surface, right? And if you ever did like oil and vinegar sort of salad dressing, it's kind of the same idea. You mix it right, it stays mixed for a bit, but eventually everybody kind of separates out, right? The oil and the sort of vinegar part, which is more like the waterish part, will separate out from each other. And that's because, again, they have really no long way of basically interacting with one another. So they really don't mix very well. In addition, pretty much whenever you try to dissolve anything in water, what you're essentially doing is there's attractive forces between one water molecule and another. So in order to sort of mix something with water, you have to break apart the water and water sort of interactions and replace it with something that's very similar. And oil is just super big. So, you know, it's kind of like you could take a big semi truck and put it in a garage. It will sort of fit, but it's going to hang out the end for a long period of time there. It's not going to really fit right. It's not going to work right. And sort of the same idea. So they really don't have a good way long-term of interacting with each other. And that brings up a really sort of common thing that we talk about when we talk about solubility of things, and that is the idea of like dissolves like. So things that have very similar, which what we're really talking about here are intermolecular forces, the way one molecule interacts with another molecule. Things that have very similar sort of those type of forces are very soluble in each other, and things that have very different ways of interacting with one another are typically going to be insoluble. So when we talk about like dissolves like, what that means is if you take something that is polar and put it together, you're in good shape. That's going to mix well. They're both going to be able to use the same type of interactions with each other that they use with themselves, so they'll be able to mix. If you take something that's ionic, like we've been talking about with the salt, and something that is polar, like we talked about with water, they also will interact well with each other. Again, basically able to do that positive, negative attraction for one another. If you take something that is nonpolar and something that is nonpolar, those guys also will be able to interact well with each other. They with each other. So this is what we mean about like dissolves like. All these things would be soluble with one another. It is only when you cross over and you take something like polar and nonpolar together, you will typically have something that's going to be insoluble in each other and really not mix. So the example of oil and water is the example of that. Oil is nonpolar, water is polar. Those things do not mix well with one another. And again, when you cross over, that's really when you run into trouble. Any questions on that there? So here is a picture of sugar up on top. And like I said before, as you can see, it is pretty much littered all over it with all these OH groups. And everywhere there's an OH group, that allows this guy, even though it's relatively large, to interact well with water, to hydrogen bond with water and interact. On the bottom there is our oil. And again, you can see it has none of those like OH groups or anything like that that's going to make it basically behave very similar to water. And that's why, again, the guy on the bottom is pretty much insoluble in water. Again, because no way to long-term interact with one another. And that is typically what we end up seeing when you take something like oil and you take something like water. Again, this guy, too big, no way to interact. And as you can see here, the water and the water guys are interacting with each other through hydrogen bonding. And again, no long period way of interacting there with that oil. So let's talk a little bit about solubility. When one substance is dissolved in another, like a solute dissolves in a solvent, it is said to be soluble in each other. So something like sodium chloride or salt is soluble in water. When one substance does not dissolve in another, it is said to be insoluble. There is usually a limit to the solubility of one substance in another, and it's also temperature dependent. At a certain temperature, you can only get so much, for example, salt to do that, or sugar to dissolve, right? If you ever took like all the sugar packets and you just keep dumping them into your drink, at some point the sugar is just going to kind of pile up on the bottom. So there is a limit. You could like heat it up, and that sometimes helps with solubility. By heating it up, a lot of times you increase a lot more energy, allowing a lot more things to break down and sort of dissolve. Gases are always soluble in one another. That's because gases are constantly flying around, which means if you got multiple gases, they're all flying around with each other. And just by that process, they're constantly mixing with one another. Some liquids are also usually soluble in each other, and that is your polar and polar guys, and your nonpolar and nonpolar guys are going to be soluble. Again, you're kind of like dissolves like in that case. These are solubility rules, which we will pick up on next time, I think. Any questions on any of that? Yeah. Say the last part again. If you were to freeze the, Yeah.
So then free salt water, more bonds form with the bonds.
Yeah. So what would happen in that case is the water would still be associated with those with the ions that are there, sodium and the chloride ions, and the freezing aspect of it would most likely actually come from the water itself with other waters freezing, and that's actually what's going to happen. And actually, it's actually a good question. Actually, if you put something like salt in water and you go to freeze it, it actually interrupts the natural process of the water coming together. So if you had water by itself and it went to go freeze, it would actually freeze at say 0 degrees Celsius. When you actually put something like salt into water and then you go to freeze it, it actually lowers the freezing point of it. And it's called freezing point depression because those sodium ions that are there, they actually get in the way of the water guys being able to get to each other. So it takes longer for those guys to get to each other and a lower temperature at which it freezes for it to actually occur. But what actually is freezing is still the water and water interactions, but they do have those ions still kind of trapped in there. It's kind of the idea of antifreeze in your car. When you put antifreeze in your car, that actually mixed with water basically, and it lowers the freezing point of your water in your car. That way, in case you live in a very snowy area, your car doesn't freeze everything inside. It also raises the boiling point in case you live in Arizona. It's really hot all the time, right? And increases the boiling point of it. So antifreeze actually does both of those things. So whenever you add solute to a solvent like water, it actually gets in the way of the natural processes of like boiling and freezing of something like water. Yeah. You're welcome.